Valence, shell, electron, pair, repulsion, theory. Part 2. We are going to see if we can do the same thing we did last time using the Lewis electron dot structures to predict the molecular shape, but then we're going to go one step further and see if we can predict if the molecule has a dipole moment. Now, if a molecule has a dipole moment, that's the same thing as saying that the molecule is polar. Now remember, in a covalent bond, which is what holds these molecules together, the electrons are shared amongst the entire molecule. And there's a tug of war going on for these electrons between the different atoms in the molecule. The atoms that are winning the tug of war are the most electronegative. So the electrons are going to hang out most often around the most electronegative elements in that molecule. These are some fancy computer-generated graphics of molecules. Notice in this red region, that's where the electrons are hanging out much more often. The blue region is where molecules are not hanging out that often. So our convention is to write a partial negative on this end and a partial positive on that end of the molecule. We're going to see today that we're also going to call this a dipole moment. Instead of using these partial charges, we're just going to draw an arrow, the little line on the end, and the arrow points towards where the electrons are hanging out the most often, where the partial negative is, where the polar end of that molecule is, from positive to negative charge. So let's take a look at some molecules and how this electronegativity difference gives rise to polarity in polar molecules. So here's a molecule that consists of two atoms, atom A and atom B. And it sets that atom A has an electronegativity and atom B has such an electronegativity, and they're exactly the same. So this molecule is not polar. So if I try to indicate if there's a polar or not, nothing happens. If I want to see where the electrons are hanging out, there isn't any red or blue because this is a non-polar molecule. However, watch what happens if atom B gets more electronegative than atom A. And as I slowly drag the cursor to get more and more electronegative, it gets a deeper and deeper red. If I want to see the dipole moment, again, start out with both electronegativities the same, and slowly make the electronegativity larger and larger and larger. So the electronegativity difference grows, the dipole moment grows. So here's a molecule of hydrogen. Do you think it's polar? Let's check. Nope, it's not polar. How about, and the reason why it's not polar is because both elements are the same. Let's pick something where they're different. Hydrogen fluoride. Is this molecule polar? You bet it is. And in fact, electronegativity is pointed towards the fluorine. And if you prefer the maps with red and blue, you can see that the electrons are hanging out much more often near the fluoride than they are near the hydrogen. So our partial charges would be a partial negative on this end and a partial positive on that end. How about carbon dioxide? Would this be a polar molecule? Let's check. Nope. Why isn't it? This dipole is canceled with that dipole. We can see that here. We have a dipole moment going towards this oxygen, dipole moment going towards that oxygen, but they cancel out. There is no net molecular dipole moment. How about ozone? Would this molecule have a dipole moment? There's the bond dipole. There's one going in this direction, one molecular dipole. There's a net molecular dipole. Take a look at the electrostatic potential map. Notice how it's more red here than it is up here. So there is a net molecular dipole moment. How about ammonia? Would this molecule be polar? Yes, most definitely. The dipole moments don't cancel. So with electrostatic potential, you can see there's a huge red hump on top. Very, very polar molecule. How about methane? This is a hard one. Is it polar? No, it's not. If you look at the map, it's not polar. It is not a polar molecule. So these are getting more difficult. So what we are going to do is we're going to go back and take a look at our valence shell electron pair repulsion theory and see if it can help us out. Recall in our valence shell electron pair repulsion theory, we had an electron pair arrangement and then we had all these molecular shapes. So let's take a look at a few real molecules and see if we can predict not only the molecular shape, but also whether the molecule is polar or not. Let's start with water. What is the molecular shape of water? You see where it falls? Definitely bent. Bent. How about the electron geometry, the electron pair arrangement? What would that be called? If we show the lone pairs, we actually have two lone pairs. So we have 1, 2, 3, 4. Our total is 4. So our electron pair arrangement should be tetrahedral. Tetrahedral. Is this a polar molecule? Definitely. Carbon dioxide. What's the molecular shape of carbon dioxide? Definitely it's linear. Sulfur dioxide. You can tell the molecular shape is bent, and it's definitely polar. Xenon difluoride. Definitely a linear molecule. What's the electron pair arrangement? Well, we need to know how many lone pairs there are. And we've got 3 lone pairs, 2 surrounding atoms. Total is 5. So electron geometry should be trigonal bipyramidal. Boron trifluoride. What's the molecular shape of this? Do you recognize it? Trigonal planar. Flat triangle. Its electron geometry. There's no lone pairs, so it's just trigonal planar. How about this molecule? Chlorine trifluoride. This has a molecular shape of T-shape. How about its electron geometry? It has 2 lone pairs, so the total has to be 5, trigonal bipyramidal. Ammonia. What's the molecular shape of ammonia? Trigonal pyramidal. See the triangular base? Trigonal pyramidal. The electron geometry? It has 1 lone pair, so the total is 4, so the electron pair arrangement is tetrahedral. Methane. Molecular shape is, recognize it? Tetrahedral. Electron geometry? Tetrahedral. Is it polar? No. Sulfur tetrafluoride. Recognize it? Seesaw. Right? Seesaw. Electron geometry? The total is 5, so trigonal bipyramidal. Xenon tetrafluoride. What's this molecular shape? Square planar. Electron geometry? Octahedral, because the total is 6. Bromine pentafluoride. Recognize this shape? Square pyramid, square pyramidal. Electron geometry. The total is 6, so electron pair arrangement should be octahedral. Phosphorus pentafluoride. What shape is this? Triangle in the center, top and a bottom, trigonal bipyramidal. Electron geometry. There aren't any lone pairs, so trigonal bipyramidal is also the electron geometry, the electron pair arrangement. Sulfur hexafluoride. Octahedral and octahedral electron geometry, because there's no lone pairs. So let's see if we can get used to some terminology here. When we say a molecule is polar, we're saying that it has a non-zero dipole moment. In other words, the molecule has a dipole moment. All of those things mean the same thing. The molecule has a dipole moment. The molecule is polar. The molecule has a non-zero dipole moment. If we say a molecule is nonpolar, what we're saying is that it has a zero dipole moment. There is no arrow that you draw on it. The molecule does not have a dipole moment. So all of those mean the same thing. So in the table below, place an asterisk by each molecular shape that results in a non-zero dipole moment. So put that star by every structure that's going to give you a polar molecule. Now, for all of these molecular shapes, they're all completely symmetric. So the dipole moments of each bond cancels out every single time. So they will never be polar. How about, there's no stars to place. How about this one? Bent is definitely polar because there's nothing to cancel these two dipole moments. Trigonal pyramidal is definitely polar because there's nothing to cancel those dipole moments of those bonds. Is seesaw polar? Well, the dipole moment with that atom is canceled with this one, but there's nothing to cancel the other two. So seesaw is definitely polar. How about square pyramidal? Is that a polar molecule? Well, the dipole moment from this atom is canceled by this one because they're straight across, and the dipole moment of this atom is canceled by this one because they're straight across. There's nothing to cancel with the dipole moment created by this bond with this atom. So this is definitely polar. We know that the bent shape is polar. T-shape. Well, the dipole moment created by this atom is canceled by the dipole moment created by that one, but nothing to cancel this one. So T-shape is polar. Square planar, these dipole moments cancel. Dipole moment created by this bond and this bond, they cancel. So square planar is definitely not polar. So as it turns out, the only ones that are polar are bent, trigonal pyramidal, seesaw, square pyramidal, bent, T-shape, and that's it. Now let's do the next part. And we'll have a complete table here for our valence shell electron pair repulsion theory. In the appropriate column in the table below, write the hybridization of the central atom for each shape. Now this isn't so bad. Let me show you why. We know that our total goes from 2 all the way up to 6. So 3, 4, 5. So electron arrangement has 2 to 6 objects surrounding it, whether they be atoms, bonds with atoms, or lone pairs of electrons. Linear, sp, is the hybridization of the central atom. For trigonal planar, it's sp2. For tetrahedral, sp3. Trigonal bipyramidal, sp3d. And octahedral is sp3d2. Now, how do I remember these so easily? Trick to this is just adding up the superscripts. We never write ones, but the superscripts always have to add up to be the total. So 1 and 1 is 2. Here, 1 and 2 is 3. 1 and 3 is 4. 1 and 3 is 4, and 1 is 5. And 1 and 3 is 4, and 2 is 6. Remember, there's only one s orbital. There's 3 p orbitals, so once you hit 3 p's, you can't have a p4, because there's only 3 p orbitals available for hybridization. So that's why you stop when the superscript becomes a 3 for P. D has 5 orbitals, so you keep going until you hit 5 for D. So usually we don't write the superscripts though. We don't write one superscript, so I'm going to erase those, make it look better. So there's my complete table. So let's try a few of these. Draw a 3D structure, give the name of the molecular shape, the polarity, and determine what the hybrid orbitals would be expected for the central atom for each of the following. Sulfur tetrafluoride. Sulfur has 6 valence, and each fluorine has 7. That's 34 valence electrons. So sulfur's in the center, surrounded by 4 fluorines. So if I make octets on those fluorines, each fluorine has 8 electrons. I have 4 fluorines, so 4 times 8 is 32. I have 2 left over. So my total is 5. And I have 1 lone pair. My total is 5, and if I have 1 lone pair, that's seesaw. My molecular shape is seesaw, and we know that it's polar. To figure out the hybridization of that sulfur atom in the center, the total has to be 5. So I have sp3, that only adds up to 4, I need 1 more, D. Here's my hybridization. So for molecular shape, draw trigonal bipyramidal first. That's the total. Remember that was a T shape? Going back, and a wedge. So, and to remove those electrons, we always remove them around the center for trigonal bipyramidal. And there's my 4 fluorines. My sulfur's in the center. So try the rest of these and see if you can get the same answer that I get. Chlorine pentafluoride, 7 plus 5 times 7, 42 valence electrons, five fluorines. Each one has 8. So that's 40 electrons. I'm left with 1 lone pair on that chlorine. So to figure out the rest of this, I like to draw the electron pair arrangement. I know that my total is 6. So I'm going to draw octahedral. When I draw octahedral, I like to draw that flat square first, and then one going up and one going down. So there's my octahedral shape. I have 1 lone pair, so there they go. And my fluorines are everywhere else. So do you recognize that shape? Square pyramidal. It's definitely polar. And my hybridization is sp3. That's only 4. I need 2 more to make 6. sp3d2. The iodine tetrachloride anion. 7 plus 4 times 7, and an extra 1. So my valence total is 36. Iodine in the center, surrounded by 4 chlorines. Each chlorine has 8, 4 times 8 is 32, so I have 2 lone pairs left on that iodine. So if I count everything up, my total is 6 again. So I'm going to draw the octahedral shape. So that was a flat square, and then my 2 wedges, one going up and one going down. And when I put in those lone pairs, remember, it was top and bottom. I had to spread them out as much as possible. So my chlorines are placed everywhere else. So the molecular shape then is square planar. It's definitely nonpolar. And the hybridization is sp3d2. Perchlorate, 7 plus 4 times 6, and an extra 1 for the charge. Total would be 32 valence electrons. So surrounding that chlorine is 4 oxygens. Oh, I forgot my charge here. It should be a -1. So around my shape here, should have a -1. Okay, let's finish this. Perchlorate, 32 valence electrons. So I have 4 oxygens. Each one has 8 valence electrons. So 4 times 8 is 32. I'm done already. So what's my total? My total is going to be 4. So I'm going to draw the tetrahedral shape. Remember how that worked? There's my tetrahedral shape. I have no lone pairs, so those oxygens just go on the corners. -1 overall charge. So it's a tetrahedral molecular shape. It's definitely nonpolar. And the hybridization is sp3. Superscripts add up to be 4, so I stop there. Thiocyanate. Hint, carbon is central. So I have 6 for sulfur, 4 for carbon, 5 for nitrogen, and 1 for the charge. So my total is 16. Octets on the surrounding atoms. So there's 16 total. That's definitely not going to be my best Lewis dot structure. So let's try moving in and making some double bonds here and see if that helps. That means we would end up with something that looked like this. Calculate our formal charges. We have 6 valence minus 2 bonds minus 4 lone electrons. That one's 0. Carbon, 4 valence minus 4 bonds minus 0 lone electrons. That one's 0. And nitrogen, 5 valence minus 2 bonds minus 4 lone electrons. -1. And that's what we want, because this entire molecule is supposed to have a -1 charge. And we could go on and try to draw some more structures, but nitrogen is slightly more electronegative than sulfur. So this is the best Lewis dot structure that we can draw. because the -1 charge is on the most electronegative atom and everything else is 0. So what's our molecular shape? Linear. Right, we have sulfur over here and nitrogen over there. Who would be polar? Because sulfur and nitrogen are not the same element. It's kind of a trick question. And our hybridization for the central atom, the sp. Okay, so hopefully you've seen how I'm kind of handling these problems. I think it's the least amount of work if you do it this way. What you do is you create the best Lewis dot structure that you can, and then you figure out what the total is. And once you figure out what the total is, whether it's 2, 3, 4, 5, or 6, draw the best shape that you can. Don't worry about lone pairs or not. Just draw that electron pair arrangement. If it's 6, draw this nice octahedral shape. And then you put in the lone pairs. And if you look at it and you draw it nicely, you can pretty much always tell what the molecular shape will be without doing a whole lot of memorizing. So good luck.